This demonstration shows how we can improve the accuracy and efficiency of software engineering tasks by computing all relevant program behaviors. A traditional analysis reasons about all paths in the control flow graph, which can be exponential for the case of non-nested branching. However, if we were to consider only the relevant behaviors for a given analysis task, the paths in the control flow graph can be collapsed to a compact graph abstraction called a projected control graph, or a PCG for short. A PCG represents the information that is necessary and sufficient to reason about an analysis task with respect to the behaviors of interest. This video demonstrates an implementation of FPCG, which computes the PCG abstraction for functions in linear time with respect to the number of relevant behaviors. Let's consider a division by zero problem. To detect a division by zero error, we must reason about all the paths to division operations that could result in zero-value denominators. In this example, there is a single division operation on line 28. Let's start by examining the control flow graph of this program. The control flow graph has 6 paths. If we construct an FPCG by selecting only the division operation as the relevant behavior, we see that the division operation happens on all paths in the control flow graph. If we were instead to choose a statement d equals d plus 1 as the relevant behavior, we would see that the projected control flow graph contains 2 paths, each governed by the condition C2, that decides whether or not d equals d plus 1 is executed. Here, the true path is collapsing multiple paths that do not execute d equals d plus 1 into a single path. Let's select the division operation and all updates to the denominator as the relevant events. The resulting PCG indicates that the condition C1 is irrelevant to reasoning about the potential behaviors for this analysis task. Let's take this example one step further and automate the entire process of producing the PCG. First, we should select all division operations in the program. Since we are only interested in the values of the denominators, we can select the right operand and a backwards traversal of our data flow graph, which represents the program's definition use chains. To select program statements as behaviors, we convert the data flow nodes to program statements by querying the containment relationships, and finally we construct an FPCG from the selected behaviors. At the end, we use a little bit of styling information to highlight the selected behavior as yellow in the resulting PCG. Now that we have covered the basic usage of FPCGs, let's take a look at a real-world application of the PCG abstraction. By implementing the FPCG algorithm on top of the extensive infrastructure of the Atlas Program Analysis Framework, which supports C, C++, Java, and Java bytecode, we have the opportunity to apply FPCGs to develop a meaningful analysis that is both precise and scalable. In operating systems, a deadlock can occur when a lock is not followed by an unlock on all program paths. If we select lock behaviors along with the corresponding unlock behaviors as an input to construct a PCG, we significantly reduce the complexity of the analysis task. Here, we demonstrate a small program in less than 20 lines of code that can be used to discover an unpaired lock in the Linux kernel. First, we select the lock instances and corresponding unlock instances as defined by the data flow relationships. In this demonstration, we focus on a single lock-unlock pairing and show the control flow graph for reference. Then, we use the selected locking and unlocking behaviors as input to construct a PCG. With a little styling information, we highlight the lock instances red and the matching unlock instances green. Upon inspecting the PCG, we see that there is, in fact, a single path that contains a lock that is not followed by an unlock. The PCG here contains 9 paths, while the original control flow graph contained 12 paths. Not only has the FPCG reduced the complexity of the analysis task, but it can also be suitable for aiding human reasoning through visual inspection. The bug in this demonstration was reported to the community and accepted along with several other bugs discovered using this technique. A complete listing of our findings and reported bugs are available online and are linked in the comments down below this video. Thank you.